Okay, last topic that we're going to talk about in detail, and this is collisions. Okay, and so when we look at collisions, it's kind of like a spectrum of what could happen, and we're going to kind of talk a little bit about the two extremes, elastic versus inelastic. But really, when it comes to all collisions, they're always someplace in between. So sometimes we get good bouncing, sometimes we don't. And sometimes energy is conserved, and sometimes it's not. And so we're going to talk about those things in a little bit of detail here in this video. All right, so again, I'm going to talk about my two extremes. Now, in the first extreme, we're looking at our elastic collisions, okay? So in other words, however much energy we give this ball, potentially, we will get in the end when we release it. So in other words, it goes down, changing to its kinetic energy, and it comes back up. And so the energy is perfectly conserved, okay? Conservation of energy holds, and we like that. The problem is that most of our collisions are not going to be perfectly elastic, okay? Our materials themselves are not going to be elastic enough to give us that extreme. But this is what we look at in an ideal sense, so we always get back to the same height. The other situation is when we look at our inelastic collisions, okay? And in an inelastic collision, the energy is not conserved, okay? So we're going to lose a little bit of that energy. So the energy dissipates a little bit along the way. Now, the other thing we like to look at is the amount of momentum that's conserved. Now, in the elastic collision sense, our momentum is always conserved. So the amount of momentum that this ball has at the beginning will be equal to the amount of energy or the amount of momentum that it has in the end. In the inelastic collision, the momentum is still conserved, okay? The momentum of this ball is still going to be conserved. It just means that part of the momentum gets transferred into our surface, and so it's absorbing some of that momentum, okay? In other words, it hits the earth, and the earth is going to move a little bit, okay? And that's kind of what we look at when we look at the conservation of momentum in our collisions, okay? So again, momentum's conserved. Energy is on the elastic side, not on the inelastic side. Okay. So again, perfectly inelastic collisions. Okay, now this is the perfect sense. All of our momentum is going to be conserved. The kinetic energy is not. Now, you might be asking and say, well, why isn't kinetic energy conserved in this perfectly inelastic collision? First of all, sound is a form of energy. Okay, so if you hear the crash, you've lost some energy, okay? And that's kind of the one thing that we like to see on that. And in fact, in most collisions, we hear something, which means we're going to lose some sound. And anytime we lose sound, we lose energy. It's kind of like friction. The other thing is that when we start to crumple material and it doesn't want to spring back, we're applying a force through a distance, okay? And so we're doing some work, which means that we're creating a little bit of energy in crumpling something. And that energy that's absorbed in the crumpling is the energy that's lost, okay? So in other words, we see a change in our kinetic energy when we're looking at perfectly inelastic collisions. So the amount of energy that we had in the end is not equal to the amount of energy that we began with. So there's a change in that kinetic energy, okay? And the kinetic energy that is lost, okay, it's not really lost, it's just absorbed by either sound or in the process of crumpling it or something like that. But now, the momentum is conserved, okay? And so here we have our car embedded into our train, okay? Prior to this collision, maybe the car was at rest. So if the car, okay, so let's go, our momentum of our train, train, let's spell correctly here. Okay. Train plus the momentum of the car before the collision is equal to the momentum of the train and car, because what happens here is the momentum, or the momentum after the collision is going to be slightly different because the mass changes. Okay, so here we have a train, and the train has some mass and it may have some velocity, and we have a car and it may have some mass and it has some velocity. In the end, the mass of the train and the car get added together to give us a new velocity. Okay, and this is like two balls coming in contact with each other, and they stick as they move off. And so we can look at it in terms of the velocity is going to change because now the mass has changed. Now, what usually happens is maybe we say the velocity of our car was at 0. Okay, it was at 0. So in other words, there was no momentum for the car. So now the train might have a mass of, I don't know, like 1,500 kilograms, okay, and it might have a velocity of 10 meters per second. And now after the train impacts the car, we now maybe have a mass of 1,800 kilograms, and so now we could find the new velocity, okay? And so that'd be an example of a problem that we could do. Okay, looking at the changes in the momentum from before versus after. Again, in elastic collision, we're going to see the masses combine, okay? Objects get bigger, okay, because they're embedded in each other, because they don't bounce, okay? There's a change in our energy because the crumpling, because of the sound, so all of that is the way that we lose our energy in that sense. Okay? Perfectly inelastic collision. Now when we look at the other extreme, we have our perfectly elastic collision. And this is the great one because momentum is conserved and kinetic energy is conserved. So we can actually look at the conservation of both momentum and energy. I chose the picture of a cue ball hitting a 8 ball, and so again, this one has a current velocity, it has a mass, and so it has momentum. So the momentum is acting in that direction. And then what happens is it's going to transfer its momentum into this, okay, which means that its velocity is going to be transferred into it. And usually what we like to see in a game of pool is the cue ball stops and the 8 ball goes, okay, and so that's what we see as a transfer of that momentum, transfer of that energy. So everything is conserved in this sense. And if I kind of look at this from a standpoint, the momentum of the cue ball plus the momentum of the 8 ball is going to be equal to the momentum of the cue ball plus the momentum of the 8 ball after. So this is my before versus after. Okay? And again, we're always looking at our situation in terms of befores and afters. Where this equal sign kind of represents collision. Okay? That's where we're actually colliding with each other. Now, in my picture here, the 8 ball is not moving. So in other words, it has a velocity of 0, which means that this whole thing disappears. In this type of collision, the objects don't stick together, okay? And this is where it's like it's like any of our sporting events. The ball itself may deform, but it actually returns back to its original shape. So again, that's where we see that conservation of energy. There's energy involved, okay? There's actual energy that forces a ball to be deformed slightly, but when it returns back, it's giving us back that energy, okay? So that's why we're conserving energy in the elastic collision sense. So now, this is the nice thing. If I look at this situation, if the pool cue ball has the same mass as the 8 ball, what'll happen here is the momentum that I have is imparted into the cue ball, or into the 8 ball, and the velocity of the cue ball will be 0, okay? That's not always the case. In fact, if you actually go through and you look at the rules of pool, the cue ball actually has a slightly greater mass than the rest of the balls, so it has more momentum when you hit it, and so it's not going to be equal. So if we said that the momentum or the mass of the cue ball was 0.16 kilograms, and it was moving with a velocity of 2 meters per second, and the mass of the cue ball doesn't change, and the velocity is, we don't know what the velocity is there. The mass of the 8 ball is probably like 0.15 kilograms, and then it might have a velocity, and we could measure, say, the velocity, maybe it comes off at say 1.5 meters per second. We could then figure out what the velocity of the cue ball is. So in other words, most of the momentum went into the 8 ball, but then there's a little bit of momentum that sticks with it. Okay, we could look at the amount of energy. Okay, so this might be my momentum equation, but I could look at the conservation of energy as well. So in other words, my 1/2 mv squared for my cue ball has to be equal to the 1/2 mv squared for the cue ball after, plus 1/2 mv squared for the 8 ball after. Okay, and so now this gives me my energy equation, and let's say I didn't know this velocity. Okay, where I had one equation with 2 unknowns. I could then have another equation with 2 unknowns, and I could solve a system of equations. Okay, so it would be feasible for me to actually find the velocity of both of the balls afterwards when I look at the fact that momentum is conserved as well as energy. Okay, so again, that's our perfectly elastic collision, and we're going to see a number of problems with that, because I know that the problem set, I think, has like 19 of those. The video that I picked today, I would suggest watching that. It's using some of my favorite music, but it does go through and give some, again, detailed notes like what I just gave here. So if you like to see it in 2 different forms, you can see it in 2 different forms. At the end of the video, though, they did a whole little dropping of various balls. They found that golf balls and mouse balls and tennis balls, and I can't remember what the third one was, but they all bounce at different heights. So in other words, we're looking at how elastic, really elastic, is that ball that they're using. All right, again, if you have questions, we'll take them in class tomorrow, and I hope you enjoyed.